Okay, great. Thank you everyone for coming along for this overview of some ocean and sea ice results. For those who don't know, my name is Roekel, the deputy lead of the water cycle group. So this is a presentation based on some water cycle version 2 results, primarily at low resolution with some sensitivity tests along the way. This is the benefit of a lot of people's work, but I want to explicitly acknowledge the help of Andrew Roberts, Leanne Conlin, Matt Maltrud, and Karthik in particular, who have provided content for, for this presentation. All right, so in a quick overview, we'll talk about a basic overview of the ocean and the sea ice in terms of code changes, capability changes, and then some comparison with observations. And then I'll spend a little bit more time on some examination I've been doing on the influence of aerosols on ocean heat content, or OHC. And at the end, we'll wrap up with an update on the AMOC group. So in V2, we added quite a few things to the ocean, but during tuning and finalization, we ended up not using many of those things. So for example, we added a spatially variable GM option, a bunch of them in fact. But we ended up, for simplicity, going back to the constant GM formulation just to make our finalization efforts a little bit simpler. A couple of the big capabilities we did add going into V2 was ready mixing. So we now have the second component of the mesoscale eddies, where we have the along isopycnal diffusion. We also discovered an advection bug in during the development of V2 that was rectified. On the left-hand panel here, you can see some of the impact of this bug for these two different simulations, this red versus the green line. Now, while they have the same scope in terms of global heat uptake, I'll show you on the next slide that the patterns are actually significantly different. The last thing I'll mention here in terms of ocean capability is an improved energy conservation in terms of tracking. So this is a plot that shows the percent change in ocean heat content uptake between the two runs I showed on the previous page. So this is defined as bug fix minus with the bug divided by the heat content fix. So what you can see is it's changed dramatically, but it just so happens that, for example, if you look in the top left panel, you'll see that we have some regions where you get much lower heat uptake and accompanied by regions where you get much higher. And this happens to work out that you get very similar globally integrated values. But this does make a big difference. We don't have a good sense yet. This is something I'm working on right now in terms of an observational comparison of which simulation is closer to observations. All right, so a few things that changed that are in the good direction in V2 would be AMOC. If you look across the top, this is V1 results from the deck. The AMOC in the upper left at rapid 26.5 north, we have a rough mean around 9 spherodrops. If you go down to the bottom left, we're now maybe closer to 10, so we've inched up a spherodrop. If you look on the right-hand panel, you'll see that in particular, the North Atlantic salinity bias is quite a bit better, from the deep, deep blue across most of the North Atlantic to slightly less blue in the bottom panel. Our belief here is this is due to our reduction of the GM parameterization by roughly a factor of 2 in terms of the diffusion coefficient. SST, some regions are quite a bit better. If you look at the top for V1 to the bottom in the stratocumulus region off of North America, you see pretty nice improvements. Other regions like the Southern Ocean actually got a little bit warmer throughout. Again, obviously the other suggests a better stratocumulus, but the Southern Ocean could be related to the GM tuning. On the right-hand panels, this is El Nino Southern Oscillation plots, where the top is V1 and the bottom's V2. It's a little bit hard to see here, but we'll see it in the next panel, next slide a little bit better. that the ENSO variability has become slightly more seasonally locked. We've moved from like 3 to 3.5 year dominant period to about 2.5. And we've lost a bit of the longer term variability in like the 4 to 6 year period. So this is a little easier to see in wavelet analysis. I've reproduced the figure from Chris's V1 paper here and made a line over the E3SM results where the dominant period is. So we're just a little past 3. Here on the right side, we're closer to 2.5. So not significantly different. And to compare with V1, I've also included some comparisons to other models from this paper by Clara Orb. The blue bars here that I'm pointing to are the E3SM results in various frequency bands. And we do really quite well in V1. These black and gray dots here are 2 observational products. And so our spectrum in V1 is actually quite nice. And we've lost, again, some variability, but it still looks pretty good. On the CI side, we made a number of improvements here. There's been a homogenization of radiative transfer, snow radiative transfer over land and sea ice. They've added some more snow layers to improve the snow morphology over sea ice, made some fields consistent with the mushy layer thermodynamics. So we have full consistency between the ice basal temperature and the thermo. Remove some daily filtering in sea surface height that was implemented for V1 that we found was not necessary for V2 simulations. So we now have true high frequency and 30-minute coupling for the low res. One really nice example here of the impact of that advection bug I showed previously are in these plots on the right, where the top panel is V1, and you can see a fairly significant amount of checkerboarding here. And this is the result of the advection bug that is really nicely improved when we fix that. Also of importance, we fixed a frazzle leak in the ocean coupling. So we have much better energy conservation here between components. Looking at the climatologies in the Northern Hemisphere, we do have a deteriorated bias in sea ice extent. If you look at the top panels here, on the top left for the Arctic and the top right for the Southern Ocean, where the blue line is V2, so you can see it's farther away from the observational line, this yellowish line. And the amplitudes, seasonal cycle amplitude is bigger, especially in March. We have increased quite a bit. There is a really nice improvement in sea ice volume here from the fixed frazzle ice coupling that spans all seasons. So comparing the middle rows here, you see the red line moving up to the blue here. And this is something we wanted to see relative to observations. The snow in the Northern Hemisphere is basically unchanged. In the Southern Hemisphere, we actually move the other direction. You can see that we lose sea ice extent here in the top right panel. There's not significant changes in sea ice volume or snow on sea ice, which from the fixes employed were expected to not have impacts. Here's some climatological maps highlighting in particular here. Andrew has put in some boxes to show where the frazzle fixes have made a significant difference. So note here along the coast of Antarctica in particular, where it's often not appreciated that there are these thick regions that are not well simulated of sea ice that we're starting to pick up. We do have some increases through the Arctic that are improved here. We're still, though, not getting buildup along the Canadian archipelago. And this is due to the low atmospheric resolution here. One other thing to mention here that we found, which is a little bit outside of low resolution, but it's an important fact to be noting here. During development, when we've run some simulations with the WC14 grid here on the right of the meshes, coupled to a low-res atmosphere, we start to see fairly significant imprinting in SSH gradients. Likely, this is due to the resolution mismatch where you could have like land grid cells with no snow and sea ice that sort of overlap with different areas of the atmosphere. All right, so with that rapid recap of the ocean and sea ice state, I'm going to move on to some analysis I did here that follows what Chris presented in November. So this is just a blatant copy of what he had shown in his all hands. So I've done this similar analysis with the ocean data. So doing a reconstruction following this middle formula here. And we're looking at ocean heat content. So in that presentation, I remember someone had asked how well this linearity assumption holds for ocean heat content in particular. So I looked at a number of depth ranges here on the left side, this left-hand panel, and it goes from 0 to 200 to 0 to 1400 as you cycle through the colors. And if you look for 0 to 300, 0 to 200, the linear reconstruction, which is the sum of those single forcing runs, matches really nicely with the historical mean. So that's the solid line versus the dashed lines for each. As you go deeper, though, the discrepancy grows as the ocean starts to play more of a role relative to the atmosphere. Interestingly, in the 0 to 700, what we can see is that as you go toward the latter half of the 20th century, you start to see the linearity match quite a bit nicer in the 0 to 700, suggesting an increased role here. So just to take a look at how well we do without any reconstruction or modulating the aerosol cloud impact, you can look at the right-hand panel here. And in particular, you can see from the blue line with the shading around it, which is the historical mean plus the ensemble variability, it compares quite nicely in the 0 to 700 layer to the data, which is a reanalysis product until the latter half of the century where we don't warm enough. So now we go and we look at, I took those parameter reductions that Chris did and just applied them directly. I didn't search for a best fit here. And this is the result we see. So if on the left is a shallower layer where linearity definitely holds, so 0 to 200. And first thing you note is that the magenta line here going through the blue is a really nice match, suggesting that in the global average, we're reproducing the very top layer of the ocean heat content anomalies quite well. Again, critical point in the average. If I start to tinker around with the aerosol effect and the greenhouse gas effect, the match is quite a bit worse, and it gets worse at 0 to 700, which are these dashed pink lines. So before going a little bit further, I should also mention I've repeated this analysis for sea surface salinity and for the overturning. Sea surface salinity had a few changes that emerged, but very few. It's hard to say the AMOC was sensitive at all to these reductions in aerosol forcing. So the critical point I wanted to make here is that although we compared well in the global average, the spatial pattern of ocean heat content anomalies does not compare well in most regions. So what you see here on the left is the reanalysis on the top. On the right is the historical mean from V2. And I've highlighted a couple regions here in particular where when we do that composite Chris put together from his talk, and that's in the V2 paper, you note that we actually start to pick up some of the observed heating in the reanalysis. So if in particular right here along the US coast, in the historical, we're cooling. When we reduce the aerosol effect, we actually pick up that warming. And similarly along the equator, we now pick up the warming signal. Seen as it's much too strong, but it's moved away from this strong cold bias. So what this means is that reducing aerosol forcing does improve the heat content, but it's certainly not the only factor because there are a number of other biases relative to the data that remain or are exacerbated when you change the aerosol forcing. So a similar pattern emerges when you go to 0 to 700. Again, you see that we primarily see a lot of cooling in the Pacific. in the historical mean, which is not seen in the reanalysis product. It's mostly warming with some slight cooling. If I just take the scaling factors from Chris just straight out of the box, we do pick up the warming, but it gets too strong. So it's possible, I haven't really tinkered around with it too much, but you could change the forcing around, those greenhouse gas knob and the aerosol knob such that you can improve this even further. But what this suggests to me is that the aerosols only play part of the picture here in the heat content anomaly, and the ocean has a story to tell in terms of being responsible for some of these biases. So switching gears here at the end, an update on the progress toward understanding the low bias in the overturning circulation. So during V2 finalization, moving forward after that, we've continued to look at this persistent low bias in the AMOC. So just a very brief recap, we had been meeting with a fairly large group of people to discuss paths forward, what data we have, what simulations we've done. And recently we've decided that we should move to a smaller, more focused team that meets more frequently so we can keep moving on this and not lose any momentum in between the weeks. So a summary of where we're at, some of the things we know for sure, is the AMOC at high resolution, what we would call it within E3SM, the 18:6 mesh, or global eddy resolving, we see a very robust overturning. So if we take that data point with the low res, this suggests to me that this is a sign of missing or poorly represented physics at low res. Something that when we go to high res, we resolve it and we get the right impacts. So this is most likely then either mesoscale eddies, and that's GM plus ready in that sense, or it could be overflows across the North Atlantic. If we start to experiment with a couple of different meshes from the cryosphere campaign, the Southern Ocean regionally refined, and then the water cycle 14 mesh, what we've seen is that variable resolution never helps by more than a sphere drip or so. It could mean we're not putting resolution where we need it. One example could be that in this, we need subtropical salinity to be sufficiently large that as the Gulf Stream moves northward, we have a significant northward salinity transport, and none of the meshes we've looked at have enhanced resolution in those gyres. I've also, along with Milena and others, we've moved and played around with the different GM options that were implemented to try and find like a best configuration. And what we found is at most we get another sphere drip or two. One thing I don't mention here is that if we change the vertical mixing from the K profile parameterization, which is the default, to a different scheme we have available, we get a fairly large jump, something like 4 sphere drips. But this is likely not directly related to the vertical mixing itself, but instead what it's doing, and I'll keep hitting this over the next few slides, is that it's helping to take some of these surface freshwater anomalies and move them to depth, because that other mixing scheme had very large diffusivities right near the surface that would move those fresh anomalies subsurface that KPP did not have. However, my sense is that's not the right solution to get those diffusivities. Instead, we move toward looking at ready isopycnal mixing parameters. So we messed around, we tinkered with some parameters there. Some of them yielded very large changes in terms of AMOC in the right direction that we want to go, but it created much larger biases elsewhere. So with that, I think the biggest unknown that could be the most critical question is why is the ocean model here so sensitive to surface freshwater forcing at low resolution? Or you could rephrase this a little bit to say, what is it missing that allows it to transport freshwater to depth. So onto a few analyses here. First from Leanne. She's taken a very wide look at GM in different configurations. So she ran a set of experiments where she goes from global GM kappas from 50 to 1800 to look at the effects. You can see some pretty big effects. For example, here in the upper right, this is an analysis of the subpolar gyre size. So in the 1800, we're pretty weak. We lose subpolar gyre in the east, and we have some still here in the west. And as we lower that down, the subpolar gyre does get better. We also see improvements in the boundary layer depth, an indication of more convection. So at 1800 here in the bottom left figure, and then the bottom right panel, you go down to 600 all the way to 50, and you start to see more deeper boundary layers. However, what we don't see is a improvement in AMOC as we go along. So this figure here in the middle on the bottom shows the vertical profile of AMOC at the rapid array, so 26.5 north. And what you see here is that we don't see significant changes as we swing this GM parameter across an extremely wide range. This doesn't necessarily mean that it's not GM. It could be that this global value is just not appropriate, and we need to look more toward horizontally variable. So we have done that. This is one such run. This is what's called the Visbeck scheme, based on a paper from 1997. So throughout this run, cryosphere coupled run, we have a robust subpolar gyre shown across the top. But what we don't see is a reasonable AMOC here. So what this suggests is that the subpolar gyre is only part of the story. The other part is this northward transport I talked about, where we may not have, and we haven't looked at this yet, a significant amount of salinity transport in this run into the North Atlantic. You can get a little sense of that from the top figures. The top figures, and more in the red here. You can see some sense of at least the transport itself, not the salinity transport. So we don't have, at the very least, a robust transport. So there's a combination of northward salinity transport and subpolar gyre strength. The salinity, we've done an experiment here, Matt did recently, with some different salinity restoring, one illustrated in the bottom left, where you have 10 times stronger surface salinity restoring in an uncoupled case, so what we call forced ocean sea ice, or a G case. And when you do that, you move from this red line in the top right to the black line in terms of AMOC. So we picked up a really nice fraction of AMOC, essentially to a number we'd be very happy with at low res. Again, the caveat being this is a G case. Interesting here that we haven't dug into yet, but the blue line in the top right is a global 10x restoring. So this, and it's slightly weaker in terms of AMOC. What that means is the enhanced salinity restoring outside of the red region in the bottom left does not enhance AMOC, but in fact seems to diminish it slightly, which could suggest we have some sort of compensating bias that happens that gets tamped down when we restore stronger. So real quick, this is just the vertical profile, the 2D stream function. The bottom right is his enhanced North Atlantic. If we could get there, it would be great. That is something we'd be very happy with. So this is a run we're going to be looking at very closely moving forward. Karthik has started to look at some ready mixing results to see the impact here. These are two such plots. The left here on the bottom is the change in salinity when we mess around with the ready coefficient itself. And you do start to see some improvements in North Atlantic salinity, some more higher salinities here along the Greenland coast. And you also get some sense that there is some improvement in mixed layer depth in the Greenland, Iceland, Norwegian seas here. But again, these runs do not show improved AMOC much. So there's still work to be done here, but it feels like we're closing in. So a quick summary. V2 Ocean looks very similar to V1, some regional improvements, some slight degradations. Tuning GM down did help the circulation and the ocean climatology a bit. The V2 sea ice had many fixes and improvements, with some improved sea ice volume in the northern hemisphere. Some degradations in extent, though. The heat content matches really well with reanalysis right now, but this is due to really anomalous highs and lows in the 2D fields. The aerosol impact does matter somewhat in certain regions, but it's not the only story in terms of the ocean heat content anomalies. On AMOC, we're making really nice progress. We still have this critical question though, but I think we're closing in. So with that, I will stop there and happy to take any questions.